Hello everyone! In today's video, I will show you how you can calculate the total drag force on a cylinder or a tower. This is required for various engineering practical problems. An example of this problem is design of wind turbine fan. An engineer has to be able to determine the total drag force to ensure that the distance between turbines is sufficient and turbines are not damaged or destroyed. For example, in this picture you can see that one of the turbines with 19.8 meters diameter is damaged. The blade came off, and it was damaged because it was placed too close to the frontal turbine, and it was within the wake region of the turbine in front. So the engineer has to be able to determine the drag force. Let's consider flow structure interactions to better understand what is the wake region behind the turbine. Assume you have a mainstream flow. If you put a splitter plate, so this is my splitter plate, immediately when flow goes towards this splitter plate, because my flow is from left to right, and as soon as the flow is approaching the splitter plate, the boundary layer starts developing. The boundary layer is the region where velocity increases rapidly from zero on the boundary and becomes approximately equal to the mainstream velocity, which I define as um. So this dashed line shows the boundary between external flow, where velocity does not change significantly, and this is your mainstream velocity, and below this dashed line is a boundary layer where velocity rapidly increases from zero to approximately mainstream velocity. If you place a structure, for example a cylinder, then behind the cylinder we have velocity profile, which will be quite different compared to velocity profile in front of the cylinder. So behind the cylinder you will have a region where velocity will be significantly reduced, and then above the structure velocity will start restoring until it becomes approximately equal to the mainstream velocity. The further you go away from the structure, velocity profile is reinstated, and when the flow is sufficiently behind the structure, velocity profile is almost the same as velocity profile in front of the structure. So this is the picture of the side view. Let's look at the same diagram from plan view. So this is our structure, which is cylinder of diameter d. As usual, I define coordinate system. X is my longitudinal coordinate. In this case, I define my origin in the center of the cylinder, and also my vertical coordinate here is my velocity, time averaged velocity. So in front of the cylinder, if you look plain view, you have uniform velocity, and then as soon as the flow reaches the structure, then behind the flow your velocity profile changes. So immediately behind the structure velocity is significantly reduced, and then when it goes away from the structure it restored and becomes approximately equal to the mainstream velocity. Then when the flow goes further away along x coordinate, the velocity profile is restored, and delta u, which is our velocity deficit and defined as the difference between the mainstream velocity minus minimum velocity, which is observed immediately behind the structure, becomes smaller and smaller. And when the distance from the structure is sufficiently far away, the delta U becomes negligible. Therefore, behind a body, there is a region which is called wake region, and this is the region of disturbed fluid downstream of the body where momentum transport is reduced, or the region of momentum deficit. So for this case, the engineer has to be able to estimate the total drag force, which can be estimated using this equation, where drag force is proportional to the fluid property, which is density, multiplied by drag coefficient, multiplied by reference velocity, which is in this case, my reference velocity is my mainstream velocity, and multiplied by reference area. In this case, my reference area is my frontal projected area of the cylinder. For the wake region, there are also a couple of more parameters which are important, and these parameters depend how far away we are considering velocity profile behind the structure away from the structure itself. And for round wake, and round wake is for cylinder of diameter d, a round wake is formed behind the structure, and there are two parameters. One is the wake region, which I defined here with capital letter R, which is the half of the width of the wake region, and this is found that this R is proportional to the longitudinal coordinate in power 1/3. So you can see that the further away you are considering point behind the structure, R is increasing and the wake region becomes wider, and also velocity deficit, which is delta U, or the difference between mainstream velocity minus minimum velocity, which is observed immediately behind the structure. And this delta U is approximately proportional to x in power -2/3. So the further away you move downstream from the structure, delta U becomes negligible. So the total drag force for cylindrical element or cylindrical structure or a tower consists of two components. First of all, it's friction drag, and also it's pressure drag. Friction drag is also defined as skin friction, and pressure drag sometimes also defined as form drag. Friction drag is due to tangential stresses on the surface, and pressure drag is due to normal stresses on the surface. So if you are considering your structure, which is plane view, which is your cylinder, and you are considering a small elemental surface area, ds, which is very small, like a dot, like a point, and on this small elemental area ds, we have friction drag due to tangential stresses, which are tangential in relation to ds. And we also have pressure drag due to normal stresses. Normal stresses perpendicular. So P is our pressure drag. Pressure, P unit area is perpendicular direction. So to find the total drag force, we need to add those two components. Depending on conditions, one component, for example, friction drag, can be negligible. And the total drag, the key contributor to the total drag, would be only the pressure drag. And this depends on the conditions or depends on flow structure interactions. So to add these two forces together, friction drag and pressure drag, you have to calculate projection of each of these force on horizontal axis, and this is in direction of the flow, and then you can add them together. So in our example, our x horizontal coordinate is defined as x, vertical coordinate is defined as z. And parameterization of total drag force is the commonly used formula which relates total drag force to the fluid property expressed through the fluid density, drag coefficient, also square of reference velocity, and also projected reference area or frontal projected area. So engineers are interested to know drag coefficient, and drag coefficient can be defined if you have laboratory experiments. You can do experiments in the lab and you can measure all the parameters on the right hand side. So you can measure force, you can measure velocity, you can calculate your frontal projected area, then you can calculate CD. And why do you need to calculate CD? First of all, when you do design as an engineer, structures that have smaller CD are more efficient. Also, drag coefficient can be used as a measure of hydraulic performance of man-made objects or man-made structures. The smaller coefficient, the more efficient structure is. And also, if you know the CD coefficient, you can calculate the drag force. Unfortunately, it's not always possible to conduct laboratory experiments to determine drag coefficient. Therefore, engineers determine drag coefficient by other means. And commonly what they do, they use various diagrams. For example, like this one. On this diagram, you can see that CD depends on Reynolds number, and Reynolds number here is defined as the product of main string velocity multiplied by diameter of the structure and divided by kinematic viscosity. And on the left-hand side, we have our CD. This is a plot diagram which is drawn in logarithmic coordinates on x and y axis, and we also can see that there are various lines. Depending what problem you are considering, you will use relevant data. In my example, I use a practical example to calculate drag force on a circular cylinder with smooth surfaces. So this will be my blue color line. If my surface of the cylinder was roughened, you can see for specific range of Reynolds number, the drag coefficient will be reduced. This is for rough cylinder. There are also lines which show drag coefficient for sphere, smooth and rough, but we are not using this. So how to read this diagram? How to read data from this diagram? Assume you have to determine the drag coefficient for Reynolds number. So we calculated Reynolds number, and now Reynolds number is 1.2 multiplied by 10 in power 5. And I will tell you how you read this. So the first number here is 10. Then you have 20, 30, 40, 50, 60, and so on. Here you have 100, 200, 300, 400, and so on. So this is our 10 in power 4, or 10,000. This is our 10 in power 5. Therefore, if we have 1.2, it means that our value is a little bit on the right hand side from 10 in power 5. So somewhere between 10 in power 5 and 2 multiplied by 10 in power 5. So approximately I just draw a vertical line which shows my Reynolds number. As soon as this vertical line crosses my smooth circular cylinder blue data line, what I do, I draw a horizontal line until it crosses the y-axis where I take or read CD value. In this example, you can see that my CD is a little bit higher than 1, but below than 1.5 roughly. So I read this approximately as CD is equal approximately somewhere between 1.1 and 1.2, for example 1.15. So now let's do a practical example. We have a 70 meters height and 10 meter in diameter smooth circular tower, and this tower is exposed to uniform wind with velocity 8 meters per second. So neglecting the end effects means the end of the tower, we need to calculate the total drag force acting on the tower. Also, we need to describe the flow pattern that will be observed at such wind speed. And for our calculations, we can use, because this is tower on the surface, on the surface, therefore it's air, and we use air density and kinematic viscosity at standard atmospheric conditions, which is 1.23 kilogram meters cube, and kinematic viscosity approximately 1.5 multiplied by 10 in power minus 5 meters squared per second. So I would like to highlight that we are considering this example uniform wind velocity. Therefore, our velocity is uniform and does not change. But as I showed you at the start of this lecture, you know that there is development of a boundary layer, and that velocity of the solid boundary, in this case is just the surface, will be coming from mainstream velocity to 0. So we need to determine the total drag force, and we will use this equation. So for this equation, we need to know velocity, which is given. We also need to know projected frontal area, which we can calculate because we have the height of the tower. We also have diameter of the tower, but we need CD. So to calculate CD, we first calculate Reynolds number, and then we will use the diagram to determine CD from a diagram. So Reynolds number I estimated as 5.3 multiplied by 10 in power 6. Just to let you know that Reynolds number is a dimensionless number, so there are no units. And for this is a very high Reynolds number, and for this high Reynolds number, there is a developed flow separation and very well developed wake region behind the tower, and this would show that the total drag on the tower is mainly due to pressure drag, and the viscous or skin friction drag is negligible. Therefore, we can calculate total drag force as our reference velocity, which is in this case mainstream velocity, multiplied by frontal projected area. And frontal projected area would be the frontal area of our cylinder, or the height of the cylinder multiplied by diameter. So let's estimate CD based on Reynolds number. And again, I show you this diagram again, but now our CD, our Reynolds number, is 5.3 multiplied by 10 in power 6. So this is our 10 in power 6. This is 2 multiplied by 10 in power 6. 3 multiplied by 10 in power 6. 4 multiplied by 10 in power 6. And this is 5. And this is 6 multiplied by 10 in power 6. So 5.3 is a little bit on the right hand side of this marker. I draw a vertical line, and as soon as this line crosses my blue data line, I draw a horizontal line and read CD values from the left hand side. And I read this approximately, as you can see, it's somewhere between 0.6, 0.7, so approximately 0.67. So now I can calculate my total drag force, which is mainly due to the pressure drag. Viscous drag is negligible. Therefore, if you put all the values which are given in the problem, you estimate your total drag force as approximately 18.5 kilonewtons. And now question for you, how the total drag force can be reduced. Assuming your weather conditions, your wind velocity, dominant wind velocity is 8 meters per second in this area. So what can you do to reduce your total drag force? I will give you a hint. You will look again back on the diagram. So this is my diagram. You can see that CD I have taken as 0.67 and my Reynolds number is 5.3 multiplied by 10 to the power 6. Therefore, Reynolds number is defined as mainstream velocity multiplied by diameter divided by kinematic viscosity. If my dominant velocity is roughly 8, the only parameter I can change is the diameter of my cylinder. If I reduce diameter of the cylinder, Reynolds number reduces. Therefore, if Reynolds number reduces, say, to around 1 multiplied by 10 to the power 6, my CD coefficient will be reduced, for example, to somewhere 0.45, and therefore my total drag force will be also reduced. And so, final question for you. So I answered this question, but I have another question for you, and I would like you to think about this. If you have ever seen around structures like this, where you can see spiral veins on the structure, and the question is, why do you think the spiral veins are used in these examples? I'm not answering this. I would like you to think and provide your comments and tell me, why do you think these spiral veins are designed and attached to those towers? Okay, goodbye. If you have questions, write your comments.